You know how sometimes you just need that shortcut? The key insights from a huge tile of information, just to feel, well, properly informed. Today, that's exactly what we're doing. We're tackling one of the toughest nuts to crack in climate action, cutting emissions from those really hard-to-abate sectors. Think long-range shipping, heavy industry, chemicals. These giants need massive amounts of energy, and just plugging them in isn't really an option. So, what's a major part of the answer looking like? E-methanol. It's this clean fuel made using renewable electricity and, crucially, captured CO2. But here's where it gets interesting. The real challenge isn't just making it. It's figuring out the best way to get sustainable CO2 from where it's captured, where the best, cheapest renewable electricity is being generated. And often those places are really far apart. Which brings us to today's deep dive. We're looking at a fascinating and I think really important new piece of research. Techno-economic analysis of e-methanol infrastructure choice for the case of Finland. This study set out to find the most cost-effective spots for making e-methanol, specifically by comparing how we transport those key ingredients.
Yeah, and what's so valuable here is that this study really addresses a gap. A lot of earlier work kind of assumed the CO2 is just there,
Right.
or they didn't fully account for the costs of moving it around. This study, though, it digs right into comparing the transport cost of electricity versus hydrogen versus CO2 in a real-world context. So for you listening, this is a chance to understand that intricate dance between geography, tech, and economics that's really shaping our green energy future.
Okay, let's unpack the bigger picture a bit. We all know the urgency, right? Cut greenhouse gases fast, and we've made great strides with things like electric cars. But what about those sectors where batteries, well, they just don't cut it?
Yeah.
Huge container ships crossing oceans, massive chemical plants needing constant energy. You need something energy dense.
Exactly. And that's where these power-to-X technologies are stepping up. They basically take renewable electricity and turn it into something else, fuels, chemicals, things you can store and transport easily.
And e-methanol is looking like a front runner there?
Definitely. This study highlights it's not just a potential shipping fuel. It could be huge for chemicals, maybe even aviation fuel down the line, but the key is green e-methanol. That means using renewable power and CO2 from sustainable sources like industry smokestacks or even direct air capture. That's how we actually decarbonize.
And get this, it's not just theoretical. There are already over 200 renewable methanol projects globally. Planned capacity. Around 199 terawatt hours by 2030. That's huge.
It really is, and about 108 TW of that is specifically e-methanol. Europe and China are big players already.
Right. Which brings us back to Finland.
Yes, Finland is a really interesting case. They're actively trying to use their big renewable resources, wind power, especially to make these higher value products for export. This study really highlights how critical it is to think carefully about where your resources are, the wind, the CO2 sources, and how the existing infrastructure fits in.
Which leads to that key question.
Where do you actually build the plant? If your best wind sites are hundreds of kilometers from your main CO2 sources, that's the puzzle this study tackles.
And you mentioned sustainable CO2 sources.
Right. You can pull CO2 directly from the air, that's direct air capture, DAC, but it's generally quite energy intensive and expensive right now. It's often cheaper to capture it from point sources where it's more concentrated, like natural gas processing plants or pulp and paper mills.
And Finland has a lot of those.
Particularly pulp and paper. The potential there is massive, maybe 19 to 110 million tons of CO2 per year, a really significant resource.
Okay, so Finland makes a great test case. Lots of wind potential up north, lots of CO2 from industry down south. This study looked at cost projections for 2030, 2040, and 2050, and they compared three main ways of connecting those resources. Option 1, CO2 transport. Basically, capture the CO2 in the south, pipe it north to the windy areas, and make the hydrogen and methanol there.
Makes sense. Keep the energy-intensive hydrogen production close to the cheap power.
Option 2, electricity transport. Do the opposite. Generate the wind power up north, send the electricity south via high-voltage lines, and make the hydrogen and methanol near the CO2 source.
Okay, so moving the electrons instead of the molecules.
Exactly. And option 3, hydrogen transport. Make the green hydrogen up north where the wind is, then pipe the hydrogen south to meet the CO2 and make methanol there.
So transporting hydrogen, which has its own infrastructure needs.
Right. And they were realistic about it. They added a 20% detour factor to pipeline distances to account for, geography and obstacles. Like the 460-kilometer straight line from Oulu to La Pinaranta becomes longer in reality.
And a really smart part of their method was how they compared the costs. Because investing in a power line versus a CO2 pipeline versus a hydrogen pipeline, they're very different beasts, different units, different scales. So They normalized everything. They calculated the total cost per unit of e-methanol produced in the end.
Ah, so a true apples-to-apples comparison.
Exactly. That lets you see clearly which overall system is the most economical.
Okay. But the suspense. What did they find? Which option came out on top for Finland? Drum roll, please.
Well, the results were actually quite clear-cut.
Yeah.
Transporting the CO2 to the electricity generation site, that was consistently the lowest cost option.
Really? Transporting the CO2 itself?
Yes.
Yeah.
Producing the methanol by sending the electricity or the hydrogen instead. That was found to be about 3 to 13% more expensive in 2030.
Wow. Okay.
And that cost gap actually widens by 2050, up to 5 to 15% more expensive. Over the lifetime of a plant, that's a very significant saving.
So why is that? What are the biggest cost factors driving this?
It really boils down to the cost of the electricity itself and the cost of making the hydrogen with that electricity via electrolysis. Those are the dominant costs in the whole chain.
Which makes sense. Renewable power is the main input.
Precisely. And the good news is the overall cost of e-methanol is projected to fall quite a bit by 2050, down to maybe around 60 to 79 euros per megawatt hour of methanol energy content.
And that's mainly because electricity costs are expected to drop.
That and the cost of the electrolyzers, the equipment that makes the hydrogen, is also expected to come down significantly as the technology scales up.
Okay, that's a strong economic case.
Yeah.
But how certain are these numbers? Projections can be tricky.
That's a fair question. And the study addressed it using something called a Monte Carlo simulation. It's a statistical method to test how sensitive the results are to changes in the input assumptions.
So, stress testing the results.
Exactly. They varied things like the cost of building power lines and pipelines. And even with those variations, the result held firm. In 100% of their simulation runs, the scenarios where CO2 was transported came out cheapest.
100%, that's pretty definitive.
It is. But the analysis also highlighted something else really important: the cost of financing. The weighted average cost of capital, or WACC. Basically, how much it costs to borrow money or get investment for these huge projects.
Ah, the interest rates and investor expectations.
Right. And that WACC had a huge impact on the final methanol cost variations of like 15 to 21 euros per megawatt hour, just based on financing assumptions. The cost of the methanol synthesis unit itself was also a big factor.
So while transporting CO2 looks cheapest operationally, the financial structure around the project is also incredibly critical.
Absolutely. It reminds us to look closely at those underlying financial assumptions.
Okay, so cost points strongly towards moving this CO2.
Right.
But as always, it's not just about the bottom line, right? This study also looks at other important factors for decision makers.
Yes, crucial qualitative points.
First off, just the sheer scale of opportunity in Finland is pretty amazing. They're seeing huge interest in wind and solar, over 250 gigawatts of grid connection requests. And Finland has ambitions to produce maybe 10% of the EU's clean hydrogen by 2030. It could become a major green energy hub.
Positioning itself almost like Norway did with oil, but for green molecules, it could bring significant national benefits.
And that ties into this bigger debate, doesn't it? Are we building a hydrogen economy or maybe a methanol economy?
That's a really interesting strategic question. Hydrogen is fundamental, of course, it's the building block. But methanol, it's just often easier to handle. You can store it, transport it using a lot of existing infrastructure. It's a liquid at room temperature.
More practical in many ways.
Arguably, yes. And it's incredibly versatile. You can convert methanol into gasoline, jet fuel, all sorts of chemicals. That flexibility is a major plus.
So beyond the direct cost from this study, what else needs to be weighed up when choosing an infrastructure path?
Well, one big one is infrastructure flexibility. If you build more power lines, that electricity can be used for anything, not just making methanol. It provides long-term options.
Whereas a CO2 pipeline?
A CO2 pipeline is pretty specific. If the industrial plant supplying the CO2 shuts down years later, that pipeline could become a stranded asset, less useful for other things.
And hydrogen pipelines?
Similar risk, maybe slightly less so than CO2, but still, if the hydrogen demand doesn't grow as expected, you have dedicated infrastructure. Electricity lines are just more adaptable generally.
Then there's safety and public perception.
Absolutely. CO2 isn't flammable, but a leak of highly concentrated CO2 near people is dangerous. It displaces oxygen. So pipeline routing and safety are paramount. Hydrogen, well, we know it's flammable and can be explosive. Again, requires very careful handling and public acceptance.
Electricity transmission lines have their own impacts, visual and land use, but maybe fewer acute safety fears compared to gas transport.
Generally, in this specific comparison, yes. Though all these technologies are considered mature and manageable with proper engineering and safety protocols, large-scale hydrogen infrastructure is perhaps the newest frontier in terms of widespread deployment.
And what about the local angle?
Hugely important. For the towns and regions where the wind farms are or where the CO2 is captured, these projects are a big deal. They mean jobs, investment, tax revenue, especially potentially in areas like parts of eastern Finland that might be facing other economic challenges.
So getting local buy-in, making the permitting smooth, that's critical.
Essential for actually making these projects happen on the ground.
Okay, so like any thorough research, this study is upfront about its limits too.
Yes, which is good scientific practice.
They focused on one main wind area and two specific CO2 sources. What happens if you look at different places, different distances? That wasn't explored in this specific paper.
Right, or different volumes of transport.
And they assumed costs for things like power lines and pipelines would stay relatively stable in their base case, but maybe building lots more power lines makes them cheaper, or scaling up CO2 or hydrogen pipelines drives down those costs.
Exactly. Future cost reductions could potentially shift the balance, although their sensitivity analysis suggested CO2 transport remained cheapest across a range of cost variations.
So it really underscores how dependent these techno-economic analyses are on the starting assumptions. Small changes could potentially nudge the outcome.
It certainly highlights the need for ongoing research and region-specific analysis.
What are the next steps then? Where does the research go from here?
Well, you could expand the scope, look at more locations, more potential CO2 sources, different scales of production. You could also compare infrastructure choices for other power-to-X fuels, maybe Fischer-Tropsch liquids, which are like synthetic diesel or jet fuel. They use different ratios of hydrogen and CO2, so the transport economics might play out differently.
Comparing different end products.
Exactly. And another big area is trying to integrate those non-cost factors more formally. Things like safety, public acceptance, flexibility, risk. Could we develop ways to quantify or weight these factors alongside the pure economics?
To get a more holistic decision-making tool.
Precisely. That would give policymakers an even richer picture.
Okay, so wrapping up our deep dive into techno-economic analysis of e-methanol infrastructure choice for the case of Finland. What's the big takeaway for you, for our listeners? It seems pretty clear that green e-methanol has huge potential, but actually building that industry requires some really smart strategic choices about infrastructure.
Absolutely. This study makes a powerful case that, at least for Finland under these assumptions, focusing on efficiently transporting the CO2 might be the most economic route. It challenges the perhaps more intuitive idea of just sending electricity everywhere.
But it's not just about the cheapest spreadsheet number.
Not at all. As we discussed, the optimal path in the real world has to balance that cost-effectiveness with flexibility, with safety, with public support, and with genuine benefits for the communities involved. It's a complex equation.
Which leaves us with a final thought to chew on. If we are serious about rapidly scaling up these green fuels, how much extra cost are we prepared to accept for those other benefits? For enhanced safety, for infrastructure that might be more flexible 50 years from now, what's the right balance? What trade-offs do you think matter most?
Something to ponder.
That's it for this deep dive. We hope you feel a bit more informed, maybe even a little surprised by the complexities involved in getting our energy transition right.